Yeah, so these days I work for this little company, Systems Approach, and our mission in life really is to sort of explain technology to people. We've been doing this through a series of open source books. We don't yet have a book on quantum computing, and you may have gathered from the introduction that Volker gave me that I'm not exactly known for my background in quantum computing. I'm known for my background in networking, and so this is kind of the story of how I came to be interested in quantum computing. And in particular, I'm interested in what impact it's going to have on the broader sort of computing landscape. And so we're going to talk about the quite a few different aspects of quantum computing today. But I just want to be very clear: don't mistake me for a quantum computing expert. So I want to actually acknowledge a couple of people who helped me with this presentation. I worked with a guy by the name of David Ott at VMware, who actually is a bit of a quantum computing expert, and he helped me put this presentation together, or at least some parts of it, when we were working together at VMware. And a lot of what I learned that you'll see in this presentation, I actually picked up from either listening to talks or reading the writings of Scott Aronson. Scott is probably one of the leading professors and theoreticians in the world of quantum computing. And I'll make some more references to him during the presentation. And then I do think I should thank my high school physics teacher, because a lot of what I understand about quantum mechanics, I actually learned in high school physics. I'm guessing a lot of you would have studied some amount of physics in high school, and you may know a little bit about quantum mechanics, and you actually don't need to know that much to be able to understand quantum computing at a high level. So I will not assume anything, but I'll just say you can go a long way with a small amount of understanding of physics. And then there's one other person I want to thank. This is Pat Gelsinger, who was my big boss when I worked at VMware. Pat, as many of you will know, used to be the CEO of VMware. These days, he's the CEO of Intel. And I got a few opportunities to interact with Pat. This is the time we went running together in China. And he is the most incredibly deep and broad technical person I've ever met. And if I ever went into a customer meeting with him, I would be sitting there thinking, I am completely useless here because Pat pretty much knows everything. But actually, after one of those meetings, I sort of made this confession to Pat that I didn't think I was bringing much to the meeting. And he said, well, actually, Bruce, first of all, you do know quite a lot about networking, and there are actually some topics that I don't know everything about. And when somebody asks me a question and I don't know the answer, I just go and find the person who can explain that topic to me, and they explain it, and then I remember it, and next time I can explain it. And I guess it's great if you can learn something that quickly and then sound like an expert on it. I won't claim to have that ability, but I do like to feel that if somebody asks me a question and I'm not quite sure how to explain it, then I should go research that and come back with a better answer next time. And that's exactly what happened with quantum computing. Because I was the CTO of VMware Asia Pacific, I was often asked questions about all kinds of technology way outside of my field of expertise. And I had to learn about artificial intelligence, and I had to learn about blockchain. And one day somebody asked me about quantum computing, and not only did I not really have a good answer for them, but I did my best to just sort of bluff my way through answering the question. And I kind of made the most basic mistake that you could make when trying to explain quantum computing. And so I'm not going to tell you what that mistake was right now, although I think you'll figure it out during the course of the presentation. But let's just say that it's good to go and do your research before answering a question, as I learned. And the person who I said really helped me understand quantum computing is this quite famous computer scientist, Scott Aronson. And if you go to his blog, which I think you can find it at scottaronson.blog or something like that. He's very easy to find on Google. Right at the top of his blog is this quote. And this is probably one of the most important points I want you to understand today, is that quantum computers do not solve hard search problems instantaneously by simply trying all the possible solutions at once. And that is roughly the mistake that I made the first time somebody asked me about quantum computing. And this mistake is very easy to make because if you know anything about quantum mechanics, you probably know something about the idea that when elementary particles are in a quantum state, they're often described as being in a superposition of multiple different states. And so we'll talk more about that. But the idea that a quantum particle could be in both one state and another simultaneously is quite fundamental to quantum mechanics. And once you have that in your mind, you might start thinking, oh, well, I could maybe try exploring all the answers at once by using quantum particles that are in multiple different states. And that is not the way it works. And so I'm going to try to explain to you how it actually does work, and then we'll talk about the implications. This mistake is so common that Scott Aronson did a whole comic strip about it. This is just a little introduction to the comic, and it's written by Scott Aronson and illustrated by Zach Weinersmith, who has a very nice collection of comics. But this is kind of a story about a parent who discovers that their child is reading magazines about quantum computing, and they're very concerned that the child is learning the wrong thing from these magazines. And the comic goes on, and you should probably go and look that one up and read it for yourself. Now, I did say I would talk a bit about the implications, and I will come back to this topic later on, but I think people often hear just one or two things about quantum computing, and so I thought I'd just bring this up early. If you've learned anything about what quantum computing is going to do, you've probably heard something about the impact it will have on cryptography. And there's a range of different views on exactly what impact it will have on cryptography. And I guess on the left-hand side here, we've got the more extreme view, which is the cryptography apocalypse. And then on the right-hand side, the slightly more moderate view, which I think is fairly close to the truth, which is that sometime in the future, it's quite possible that our existing cryptographic algorithms will be compromised by quantum computers. And if you read the fine print there, it says 25 years. And we'll talk more about that. So again, just a high-level message here is that cryptography is one of those areas that will almost certainly be impacted by quantum computing, provided we keep on making progress the way we have done in the last 20 years or so. So I thought you should have a look at a quantum computer. This is a fairly typical quantum computer. I think this is the one from IBM, if I remember correctly. And so a couple of things to notice about this. This is a reasonably big quantum computer by today's standards. It's about the size of a refrigerator. And in fact, it is not just the size of a refrigerator, it actually sits inside a refrigerator. It's quite a special refrigerator. It's a refrigerator that can cool things down to 15 millikelvins. Now, hopefully most of you know that 0 Kelvin is the coldest possible temperature, and in fact, it is impossible to get to 0 Kelvin. You can only asymptote towards 0 Kelvin. So 15 millikelvins is extremely cold. It is minus 273 Celsius, and it is colder than the deepest, coldest parts of space. It is exceptionally cold. This is the way we get to observe the behavior of quantum particles for reasonably long periods of time, is to cool them down so much that they don't interact with their environment. So this is about getting everything to be extremely still and stable by lowering the temperature so that you can get these quantum particles into a state where they will maintain coherent quantum behavior for a reasonably long period of time before they bump into something and sort of collapse their quantum state. Don't worry if all those terms don't make sense to you, but just take away, this is a very, very significant piece of engineering just to build something that can get particles into a quantum state for long enough that we can observe what's going on and do interesting manipulations with them. Now, how did I come to be interested in quantum computing? Well, I've already told you half the story, which is that somebody came up to me, asked me a question, I gave a terrible answer, and I decided I would do better next time. So I started reading about quantum computing maybe 4 years ago, but then in 2019, I was off on a business trip, and I did what I normally do when I'm traveling by myself on business. I went to the pub, I bought myself a beer, and I sat down and I started reading interesting things on the internet. And this is a great way to make sure that nobody ever bothers you. If you sit down and read about quantum computing, you can pretty much be left alone for the whole night. So at some point, I came on this article that said Google has published a claim of quantum supremacy. Now, quantum supremacy, or sometimes called quantum advantage, is this idea that a quantum computer can do things that can't be done by a classical computer. And maybe when we say can't be done, can't be done in a reasonable amount of time with a reasonable amount of power in a reasonable amount of space. And so in 2019, Google made this claim that they had solved a problem in a few minutes that would have taken about 10,000 years to solve on a classical computer. And so when I saw this, it certainly got my attention, and I immediately went to Scott Aronson to see what he had to say about this topic. And by the way, I kind of knew who Scott Aronson was, in part because he was at MIT, I think maybe 10 years ago. These days he's at Austin. But so I had seen him give a talk once, and I knew that he was kind of not only the expert, but also a very good explainer of this topic. So I went to see what he had to say about it, and he had a very nice comment, which was there was a lot of controversy about this claim, and he said, "So is this a big overhyped nothing burger?" Well, it's not an everything burger, but it's at least a something burger. And for those of you who don't speak English as your first language, I hope this all makes sense. But the idea is that there was a claim made by the people at IBM that in fact Google had not really achieved anything very much. Now, IBM is a big player in quantum computing, as is Google. So this was a bit of a fight between two of the giants in the field. What IBM was able to show was that if they took their biggest classical computer, which is about the size of 2 basketball courts, and gave it the weekend to tackle this problem, it could probably do the same thing as Google's quantum computer. So whereas Google had said 10,000 years, IBM said, well, we can do it in the weekend, but it's still a massive computer that is the biggest supercomputer in the world. And so there was definitely a very significant result here. Now, to be fair, the particular problem that Google solved is completely practically irrelevant. It's not an interesting problem for anybody. It's simply showing a simulation of quantum behavior that is very difficult to simulate in a real computer, classical computer. And so they sort of constructed this very artificial problem and then said, look, we solved it. It's quantum supremacy. So that kind of gives you a sense of the state of the art as of 2 years ago. We'll talk more about solving practical problems, but this is a big deal. I would say, some people have compared it to the Wright brothers getting their first heavier than air plane off the ground. It didn't go very far. It didn't much like anything that anybody would ever want to use, but in fact, it was the beginning of of the era of powered flight. And so I think that's kind of where we are with quantum computing. We're just in the very, very early stages of showing that some useful things can be done with quantum computers. Okay, so I'm going to try to explain in the next 2 or 3 slides roughly how a quantum computer works and how it can do things that can't easily be done on a classical computer. And so I hope you've all heard of Schrodinger's Cache. This is the very classic thought experiment that was created by Schrodinger in trying to help us conceptualize the superposition of different states that occurs when we're looking at elementary particles exhibiting quantum behavior. So the idea of Schrodinger's cache was, you could construct a box, and inside that box you could put a little vial of poison that could be set off by the decay of a radioactive particle. And at any given point in time, that radioactive particle has either decayed or it has not decayed, and we don't know which of those it's in. So it's effectively in those two states. It's both decayed and not decayed until we measure it. And so if the whole box is sealed off and we can't observe it, then the claim would be, well, the cache is both alive and dead until we open the box. And then when we open the box, the quantum state collapses. So it goes from being both alive and dead to being in just one of those two states. So that's what I mean about coherence, is where we can maintain the superposition of different states, and then the collapse of those states is when we measure them, we're only going to get one outcome. Now, this experiment, as far as I know, has never been done. It doesn't really make sense because there's too many things of, the cat is quite aware of what's going on. There's interaction with the real world, so it's not really a true experiment. But the thinking is, understand that an elementary particle can be in two states at once, and it really can be in both states at once until you measure it, and then it will collapse into a single state, and that is the essence of quantum mechanics. And the really good example to explain this is the double slit experiment, and I'll come on to that in a moment. But before I go there, let me just explain how we can use this property of quantum mechanics to build an interesting computer. So you all know that in a classical computer, a bit is either a 1 or a 0. And we very carefully design our digital computers so that we have like a voltage level for 1 and a different voltage level for 0, and there's a little gap between them, and we always know that a bit is either 0 or 1, and it's in exactly one of those two states. Conversely, in a quantum computer, we very carefully construct the environment so that we can have a particle that is in both what we would call a 1 state and a 0 state at the same time. And exactly what constitutes a 1 or a 0 could be a few different things. It could be the position of the particle within some constrained environment. It could be the spin of an electron, which could be either up or down. There's a bunch of things we can use as 1s and 0s, but the interesting thing about a particle exhibiting quantum behavior is it can be in the superposition of the 1 state and the 0 state at the same time, as long as we haven't tried to measure it. And so the essence of quantum computing is to control the way in which we put particles into these superpositions of different states, and then we keep them in that state while we do manipulations of them, and we try to maintain that for long enough to do an interesting calculation. And at the very end, we make a measurement and we see what we got. But the key idea is get things into these sort of mixed states, have them interact with each other, and then at the end you measure what you got. So I'll try to explain this. Oh, and just to maybe just say one more thing on this picture. So you can think of the top of this sphere as the 0 state, the bottom of the sphere is the 1 state, and a quantum bit or a qubit, we can put it into any position we want to on that sphere. So it doesn't have to be just at the top or the bottom. We can put it on the equator, we can put it halfway between the equator and the top, or halfway between the equator and the bottom, and we can manipulate where it is. And these are all the operations of a quantum computer. So for an example, one operation you can do is you can effectively say, rotate the bit through 90 degrees. So that'll move it to the equator. Now it is clearly half 1 and half 0. And then you can say again, rotate it through another 90 degrees, and it will go to the other end of the sphere. And so you can do these kinds of operations, and this is what gives you the sort of power of quantum computing. And one of the things that you would notice here is that if I wanted to describe the state of a single qubit, I need to describe exactly where the qubit is on this sphere. And that position can be roughly described by two coordinates, latitude and longitude, if you like. So the amount of information I need to represent a single qubit at any point in time is roughly two real numbers. Now, imagine that I had a computer with 50 qubits. If I want to describe the state of that 50 qubit computer, I would need to have 2 to the n numbers to describe all the possible states that it could be in. And 2 to the n is pretty big at 50 qubits, and it gets really big at 100 qubits. And so this is how describing the state of a quantum computer becomes very difficult for a classical computer, and very quickly gets to be so much state that we can't actually do it in an existing classical computer. This is exactly what Google did. They created a program to simulate a quantum circuit. They ran it on their quantum computer. The quantum computer is very good at that job. Meanwhile, doing it on a classical computer requires, at the very least, an entire weekend on the world's biggest supercomputer, or maybe 10,000 years on a slightly smaller computer. So if you wanted to get a bit of intuition about why quantum computers are different than classical computers, it's the complexity of the state. And maybe just one more bit of interesting stuff here is that we can actually entangle the state of two qubits so that they could both be in this kind of indeterminate state where we don't know if they're 1 or 0, but if I go and measure one of them and it turns out to be 1, then at that point I know the other one's going to turn out 1 as well. That's kind of how entanglement works. It's pretty freaky once you start to dig into it, and entanglement is part of what makes the behavior of a quantum computer so difficult to simulate in a classical computer. So at the very least, all I've told you really so far is that it's very hard to simulate a quantum computer with a classical computer. The bigger question is, can you do anything useful with a quantum computer? And the answer to that is yes, and we'll get there. Okay, this is the last little bit of physics before I go and jump into some of the applications. So hopefully a lot of you have heard about the double slit experiment. It's the most important experiment to understand quantum mechanics. Feynman, the famous physicist, said, if you understand this, you understand most of quantum mechanics. And so let me just walk through it real quickly. If we didn't have quantum mechanics, if we just had classical behavior, then the world would look the way this picture looks on the left. You could take a bunch of particles, you fire them at a screen with two slits, and they would show up on the wall or on the detector in these two bands. That's what you would predict if you could say, well, any given ball is going to go through either the top slit or the bottom slit, so we're just going to get two stripes based on which slit the ball went through. That's not what happens. If you fire something really tiny, like an electron or a photon, at a screen with two slits, you get a picture more like what's shown on the middle here, where you get these series of bands. And the series of bands correspond to a summation of probabilities based on the possible path the ball could have taken. So it could have gone through the top slot, or it could have gone through the bottom, and it could, having done that, could have landed in a range of different places. And if you add up these probabilities, they have this interesting property that the probabilities can be both positive and negative in the quantum world. And if you add up a positive probability with a negative probability, you get zero probability. And that's what gives you those dark spots on the detector. And then if you add up a positive probability with a positive probability, you get a positive, and that is where you get the bright spots. And actually adding a negative to a negative gives you a strong negative probability, but that turns out to be also positive. So at least the magnitude of it is positive. So this is the picture that you get on the detector is actually a summation of probabilities based on the fact that a ball might have gone through either of those two slots. As soon as you close off one of the slots and force all the balls through, or all the particles through one slot, you go back to a picture like the one on the left. Even if you try to measure the particles as they go through the slot, you get the picture on the left. If you don't leave open the possibility of a particle going through both slots, then you won't get the picture with this series of dark and light bands. So the only reason why we get this series of dark and light bands is because the photon or the electron has the possibility of going through either slot, and it actually behaves as if it had both options all the way until it hits the detector. As soon as it hits the detector, we've collapsed those possibilities. And if we even try to do a simple measurement before it hits the detector, we collapse all the possibilities. So this is the stuff about quantum mechanics that's kind of painful to understand, is as soon as we measure what's going on, we take away a set of possibilities, which causes the quantum behavior to vanish. You open the box, the cat is now either alive or dead. You measure the photon, you now know which slot it went through. You no longer see this interesting picture on the right. So what quantum computers are doing is they're preserving the possibility of going through both the top slot and the bottom slot. They're preserving the chance to be both a 1 and a 0 at the same time. And they do that for multiple calculation steps. And at the end, you get an output from the quantum computer that looks a little bit like this pattern of dark and light bands. You actually get some outcomes that reinforce each other, and you see that those get output by your quantum computer. Other outcomes cancel each other out, so they don't get output by your quantum computer. And it's things like this that actually help us run meaningful algorithms on our quantum computer, and that's what I want to talk about next. So there's a really broad range of problems that seem to be well suited for quantum computing, and some of the most obvious ones are situations where you want to really simulate quantum behavior, like chemistry. You want to understand how an atom is going to behave? Well, you really need to understand quantum behavior to properly model the behavior of an atom or a molecule. So chemistry is a field where there's a lot of applications for modeling the behavior of atoms and molecules using quantum computers. So that's one you've seen, lots of publications about that. In general, optimization problems are often about kind of searching through a big space of different possible outcomes. And so quantum computers turn out to be pretty good at that. This is one example of searching for the ways in which cancer sort of mutates to produce particular outcomes. And this is another example where it's effectively a sort of searching for the correct answer amongst a very large set of wrong answers. And you can sort of think about when we have problems like that, we can set up things like those dark and light bands on that double slit experiment. We want to try to make the right answers be where we get lots of probability and the wrong answers where we get not much probability. And so we can set up these kind of search type problems using a careful construction of quantum operations. Machine learning is another one. If you probably know that when you're training a neural network, part of what you're trying to do is you're trying to find a good set of weights for your neural network. Again, it's kind of a search optimization problem. And so quantum computing turns out to be good for that. Again, sort of searching through all the different possibilities, trying to find the good ones. We're trying to set up our quantum computation so that our good weights are the ones that get output by the quantum computation. And then the one that I kind of hinted at the beginning of the talk is public key cryptography. And this is one which I think, there's a good reason to be thinking about this sooner rather than later. As far back as 1994, this guy by the name of Peter Shaw came up with an algorithm to use a quantum computer, even though they did not exist at the time. They were theoretically conceived of, and so he came up with an algorithm to find the prime factors of an integer using quantum operations. And this is really important because these problems of factoring big numbers are believed to be very, very difficult on classical computers, and a lot of the internet depends on the belief that these things are really, really hard to solve. So when you create a certificate to secure a website, it depends on public key cryptography, and at the bottom of public key cryptography is the belief that it's very hard to find the prime factors of a very large number. So Peter Shaw came up with this idea that you could use a thing called the quantum Fourier transform, which is actually a very simple operation to do in a quantum computer to find the factors of an integer. And this has already been shown to work on the quantum computers we have today. It's probably worth mentioning that the numbers that people are being able to factor at the moment on quantum computers are quite small because quantum computers are quite small, but the principle has been proven to be solid. And so the National Institute of Standards and Technology in the United States has been looking into this for quite a few years, and they've come to the conclusion that most of what we use today for public key cryptography will not be secure once quantum computers get big enough. And we'll talk in a bit about what big enough means. Bigger than we have today, but not so big that we don't believe they're possible. Okay, so we're thinking maybe 4,000 qubits would be a big enough quantum computer. And again, today, 100 qubits is kind of roughly the state of the art. So there is an effort to come up with what's called post-quantum cryptography, which is to try to find algorithms that work in a similar way to the ones that we use today, but that don't have this vulnerability to quantum computing solutions. And here's some of the people who've worked on it. And so last year they came up with some candidate algorithms. And this is a field of really active research for people who understand things like computational complexity and algorithms at a very deep level. And it's not something for the faint of heart, but it is something where there's a lot of intellectual heavy lifting going on at the moment. So just to give you a high-level understanding of what we're trying to do here, the way public key cryptography works today is, if you have a private key, it's very easy to calculate your public key, and you can effectively do it by multiplying a couple of numbers together. But to go back the other direction, you have to do this very difficult thing, which is figure out what were the prime factors of that big number. And so that going from private to public is easy, going from public to private is hard. That's why it's easy for me to sign a document with my digital signature and hard for somebody else to fake it if they don't have my private key. But again, these functions that we depend on that are believed to be easy in one direction and hard in the other, they turn out to be not hard once you have quantum computers of a suitable size. There's an emerging type of cryptography based on lattices, and these are just a new class of algorithms that they still have this property that they're easy in one direction and hard in the other, but they don't seem to be amenable to quantum solutions. And I think this gives you a good sense of why Scott Aronson is so keen to point out that you simply don't get to try all the answers at once when you're running a quantum algorithm. You get to do very carefully controlled things to set up something like the double slit experiment on a bigger scale. And with that, you can run an algorithm that's efficient, but you don't simply go and brute force the solution to find the answer. So should we be worried? Well, so, today we're sort of in the middle of this picture. We have these quantum computers that are going at about, 100 to 200 qubits. We can see a pathway to having multi-thousand qubit computers within the next few years. And so we could expect maybe by the end of this decade that we will have quantum computers that can break the current cryptography. And so we need to be doing this thing called quantum readiness, where we start thinking about this today, because it's not easy to change algorithms. You have to change a lot of code, a lot of websites, a lot of software systems. And also, if you are encrypting something today and storing it, or if your adversary is capturing it and storing it, they may be able to decrypt it in the future. Okay, so what's going to happen next? Well, first of all, people are going to program these computers, and this is a question I often get, so I'll sort of just give you a little sampling of what the code looks like. Now, if you look on the left, it looks pretty much like, C code. If you look on the right, the comments are a little bit weird. So we're doing things like allocating qubits. We're doing a Hadamard transform, which is actually like that rotation that I talked about earlier. It's also a bit like a Fourier transform. We're doing another kind of transform. And then I really love this line. This expands the entanglement to the third qubit. So we can literally say, I want to entangle a set of bits and cause 3 different bits to have a state where they're all in this indeterminate state, but if we measure one of them, we're going to find out the state of the other one. That's a crazy thing that you should go read about quantum entanglement and figure out just how hard it is to get your head around. But the fact that we can do that in today's quantum computers is fundamental to what makes them so powerful. And at the very end, we measure it. And so we maintain this nice quantum state where all the possibilities are open to us. And then at the end, we measure, we collapse everything down, we get a measurement. And if we do enough measurements, we can build up things like the pattern of dark and light bands that we saw in the double slit experiment. I'm saying that as sort of a metaphor, but effectively the good answers, the correct answers will reinforce each other. The incorrect answers cancel each other out. That's how we can do things like integer factorization. And this is not a quantum computer. This is a different kind of special computer. This is Google's tensor processing unit, which is used for doing things like a large-scale machine learning. But I think the overall picture is very similar, that we will have quantum computers that they're going to be complicated and expensive. You're not going to have one in your pocket, but they will sit in data centers, and people will use them by connecting into the data center and putting in code like you saw on that last slide, and getting access to these amazing capabilities that are, maybe you don't need 100 of these things initially, but people will get access to them as a cloud computing service, much the way we do for things like machine learning today. So this is my final slide. What's going to happen? Well, I don't know, but I think that there will be more and more applications. I just showed you a few. We do have to think about cryptography. That is an immediate concern, and there will be new algorithms coming, and that will cause quite a bit of upheaval in the networking business, in the web security business. So there's definite things we can see happening there. And what else? I really don't think it's easy to say, but I hope you understand now that these computers are unlike anything else we've ever had. A GPU or a TPU is just a very clever classical computer, very well specialized for its job. A quantum computer, it's a whole different thing. And it's something we've dreamed of for quite a few decades now, and we're just now starting to see the impact of them. So that's all for the formal presentation, and I'm happy to do a bit of Q&A.